For decades, scientists have relied on global maps of nighttime lights to track the advance of human infrastructure. Our ability to measure light pollution and its ecological impact depends entirely on the assumption that these historical datasets remain continuous over time. But that continuity is currently collapsing. Cities worldwide are executing a massive infrastructure shift, replacing older high-pressure sodium, or HPS lamps, with modern white LEDs. This creates a severe physical deception. If you point a generic sensor at an orange HPS lamp and then at a white LED, the distinct physical wavelengths enter the lens and get flattened into a single panchromatic output. Two completely different light sources produce the exact same number on the screen. Physicists call this the principle of spectral non-equivalence. It dictates that panchromatic measurements cannot tell you what kind of light you are actually looking at. If the data outputs look stable, but the physical composition of the light hitting the environment has shifted from narrow sodium spikes to broad LED peaks, our historical models of ecological and astronomical light pollution are mathematically blind to reality. To understand the scale of the error, we have to examine the specific tools professionals rely on to track the night sky. The most common are ground-based sky quality meters, or SQMs, and the orbital VIRES-DND satellite sensor. Every light sensor has a spectral response curve. This is the specific, limited slice of the light spectrum that a given device is actually physically capable of detecting. This chart maps the exact spectral response curves of our critical legacy networks. The ground-based SQM and TESS-W sensors sit close to the visual green region, while the orbital VIRES-DNB sensor is shifted far to the right, toward the red and near-infrared spectrum. This chart shows the baseline spectrum of high-pressure sodium lamps. The narrow spike distribution our sensors tracked. When a 4,000 Kelvin LED replaces it, a massive peak emerges in the blue spectrum, near 450 nanometers. Because this massive blue spike falls almost entirely outside the peak sensitivity ranges of the legacy curves, especially the red-shifted VIRES-DNB, the sensors simply do not register it. They are virtually blind to the most significant physical change in the environment. These historical networks are strictly panchromatic. Because they cannot separate light intensity from spectral composition, they're physically incapable of detecting the true magnitude of the global LED transition. If the old hardware is blind to the new light, the logical question is whether we can fix this in software. Can we build mathematical models to convert outdated single-band readings into modern multispectral data? Researchers tested this by attempting to transform single-band output values into standard multiband arrays, like the CIE XYZ system used for human vision models, or the Johnson-Coulson system used in astronomy. Attempting this forward transformation using a historical HPS calibration fails catastrophically when applied to modern LED lighting. This heat map matrix displays the empirical bias percentages when SQM sensors infer target bands under different lighting transitions. When an SQM calibrated on HPS lighting infers the blue-sensitive CIE-Z band under a white LED, it underestimates true radiance by 76%. The equivalent heat map for the orbital VIRS-DNB sensor proves this failure isn't isolated to ground stations. The variance is extreme. VIRS data underestimates the CIE-Z band by 84%, while simultaneously overestimating the Johnson-Coulson's B band by 102%. In mathematics, this is known as an ill-conditioned problem. Extracting a complex, multispectral reality from a single panchromatic number is mathematically impossible without making massive, unsupported assumptions about the source light. Standard industry practice, applying old single-band calibrations to a modern lighting grid, is quietly injecting massive statistical errors directly into global environmental datasets. Does this mean decades of meticulously gathered legacy data from single-band sensors are now completely worthless? Not entirely. The math actually works perfectly if you reverse the direction of the transformation. This concept is called the asymmetry of radiometric inference. While you cannot accurately guess a complex spectrum from a single number, converting down from a modern multiband measurement to synthesize a legacy single-band measurement is a highly stable, well-conditioned mathematical operation. This heat map visualizes the recovery of legacy data using inverse synthetic photometry. The deep purple colors indicate highly stable operations with extremely low error. Synthesizing data from a multiband system like SDGS-SAT consistently produces median errors tightly between 0.6 and 3.6%. This proves that modern systems, from standard consumer DSLRs to satellite RGB arrays, can mathematically recreate exactly what a legacy sensor would have seen. We don't have to throw away the historical record. To keep the historical bridge intact, we simply must transition to gathering all new data using a multiband foundation and calculate backward. To operationalize this math, researchers have proposed a formal policy solution, the multi-level Allen-Q standard. Rather than mandating a specific brand of sensor, Allen-Q provides a strict 4-tier hierarchy defining how radiometric transformation matrices can be used. The first tier, Allen-Q1, is explicitly designed to quarantine calibrated single-band legacy instruments like the SQM and TESS-W. Under Allen-Q1, the regulatory rule is absolute. Legacy sensors are strictly limited to tracking historical, order-of-magnitude trends exclusively within their own specific band. Q1 data must never be used to infer color or predict physiological impacts on wildlife without explicit, documented auxiliary assumptions about the lighting spectrum. This tier preserves the value of our historical time series records while preventing their spectroblindness from infecting modern ecological and astronomical models. The higher tiers of the standard, Allen-Q2 and Allen-Q3, establish the strict foundation for modern multiband monitoring using platforms like DSLR networks or SDG-SAT. Both tiers utilize the same multiband equipment, but they are separated by strict metrological validation rules. Allen-Q2 designates scientific precision. These are multiband setups calibrated dynamically in the field. Allen-Q3 requires SI traceable legal precision. This tier demands formal, auditable chains of evidence verifying the absolute calibration, reserved specifically for regulatory enforcement and government audits. Finally, Allen-Q4 serves as the absolute full-spectral spectroradiometric reference point. Instruments in the Q4 tier are not designed for bulk data collection. Their sole operational purpose is to synthesize any possible band and continuously validate the mathematical transformation matrices relied on by our 3 tiers. The global transition from high-pressure sodium to LED street lighting forces a critical realization about how we monitor the night sky. Spectral uncertainty now introduces more error into environmental datasets than the physical sensors themselves. Modern light pollution monitoring must be inherently multiband, explicitly linked by versioned radiometric math. Without that spectral foundation, environmental science is flying blind.